Just okay. I know. We're starting. Yeah, very good evening to all. Yeah, welcome to the special seminar of the physics special seminar. So today here Dr. Aditya is here. So he's from for nanoscience and engineering from ISC Bangalore. So who have completed his Cambridge. Then he continued as a postdoctoral fellow over there. Then in 2019, he joined as a faculty at ISC Bangalore. So he's working on perovskites. This small introduction, I would like to ask Dr. Aditya to start his presentation.
I'll check, mic check. Am I audible? Okay, great. So thanks for the question and the kind introduction. This was kind of a very sudden trip, not planned. Is here for an event tomorrow, and I happen to accompany here. So I thought I'll make use of my time here. So my first visit to ISER and IIT at the same time. So there is a history associated. So basically, if I would have not joined IIC, I would have been here. So I had to decide very hard whether I would join here, join there. So later, well, it was hard. Think that you don't want to join the major IITs or even the major ISers. So the decision was against the older institutes, IISc being one. So I joined the department there, so that compensated for that, basically. So anyway, so glad to be here. I mean, I know few faces here. So students who work with me for their internships continue to be engaged. So today I'll be talking about something we are doing at IISc. Now this draws major inspiration from my work during my PhD itself at Cambridge. So this is a spectroscopy technique we built at Cambridge. Continue to build the second version at IISc. I'll show you few results. What are we doing as a major topic and how this is applicable to various different. So we'll just focus on the application bit more, some basics and mostly applications. We also work on various other topics. I'll run you through that. Before I go, customary slides because I come from this place. So this is Center for Nanoscience and Engineering, the department where I work at IISc. And this is one of the national hubs for nanoscience and characterization based activities. Currently, this is the only ISO certified lab, fab and characterization in the whole of India. So it has some reliability associated with it. So, and here we have like the major thing is the clean room, massive academic clean room there. And there are a lot of instruments inside, and we are like around, as of today, we are 19 faculty. So one new person has joined us. We have the same strength of as in ISER Tirupati. I just heard 150, so we are close to that as of now. Department there, and the key thing is we have 150. I say 130 here, but the real count is 150. And the staff members after the facilities. So the facilities essentially are independently run. Please don't look after them. So that's what makes it mostly national and equally available for all of you guys. So so I'll not go much into it. So we run MTech program, we run a PhD program. So all the undergraduates here, please do think of these programs. Uh, they come with a lot of advantages. I urge our website, which has been modified, keeping in mind the ease of access. In terms of research in our department, we are an interdisciplinary department. So we run various verticals coming from semiconductors all the way to bio, chemistry, a lot of areas. So we have a lot of interdisciplinary folks in our department. So like myself, I'm an electronic engineer. I did my master's in nanoelectronics, then moved to PhD in physics, and I work here. So I have a different view of things. Likewise, there's some other faculty who was an aerospace engineer working at NASA, and now he works on biology. He detects DNAs. Okay, he works on DNA sequence. So likewise, there are a lot of interdisciplinary areas. So we try to touch upon the niche things between different interfacial verticals. And one of the key aspects of our department is working with industries. So a lot of these industries are semiconductor focused industries, hence this India Semiconductor Mission. We are one of the major contributors to this. We have trained the first batch of Tata engineers to basically run the fab that is coming up in Gujarat. Okay, so these are all the companies we engage with. And coming to my research now. So in my group, we basically work on thin films, optoelectronics, and sort of looking at various things you can do around this field with light and devices being a key theme. And we mainly work on solar cells and LEDs. That's one major areas, but we also work on other detectors. There are lot of issues surrounding these areas which I have summarized here. In terms of materials, we work on organics, so that's something which probably relates to you. We work with perovskites, that's one of my major areas, relates to you there. And we also work materials because we are an interdisciplinary bunch in the department, so we have access to various inorganics. And so this is about how research works in our group. But in terms of activities do, so we basically have all these activities running. So we start with materials. So we borrow materials in case we don't make it. We make our own perovskites there. And then we go into the characterizations and the devices, and this is the loop that you follow. So these are all very well interconnected. Today, we'll be talking about this part here, okay, and how it connects to the other parts in the loop that you, okay. So that's the outline. So I'll talk about PDS. So we'll talk about absorption, basic, because I'm told I'm talking mostly to undergrads. Can you raise your hand who are undergrads here? Undergrad? Okay, great. Yes. I love the spirit. So, masters? No. Okay, few. Okay, so it's a mixed audience. Fair enough. So, I'll start with absorption, some basics. So, how many of you know absorption? Most of you do. Okay, there is half-hearted attempt there. Okay, issues. So, you're trying to measure the absorption spectrum any material. It could be a semiconductor, it could be anything else. I mean, catalyst or whatever. So what you try to do here is you shine a known spectrum of light. So it could be white light, and you essentially absorb some light in your sample. That's based on the absorption property of your sample, and the remaining comes through as a transmitted portion. So you essentially know what went in, what came out, so you know what got absorbed. Okay, so this is the way the traditional transmission spectrometer works. So probably you would have these sitting in universities or even individual labs as such. Now, this is a way of measuring, but what we do is very different. So we basically measure in this spectroscopy technique called photothermal deflection spectroscopy. Why this name actually is such and not just mere absorption. So this relies on this image what you see here, and probably at Tirupati this is not so uncommon in summer. I guess you go out on the road, you'll see this pretty everywhere. So now how this happens is mirage happens because your surface of the object is very hot and the surrounding slightly colder temperature. So you have a temperature gradient near the object. Have light rays coming from far off, they actually bend off the object and then your eye, which makes you see clear images. So you see, but when you go close, these light rays are at acute angle, they can't bend much. So you see, so that's why the mirage exists far away, not close to you. Now, make use of, but I'll tell you how. So if you go to basic semiconductor, let us say you have your basic valence band conduction band and you come in with two photons, and these two photons basically can excite two electron hole pairs, and do nothing, these electron hole pairs should relax. Okay. And that relaxation can again happen in two ways. So one of the ways is you come down, you emit a photon. Okay, so you give back the energy. And the other way is you do come down, but you basically emit heat. So this is phonon assisted. So we make use of this heat part. So I am explicitly relying on being generated upon absorption. Okay, so take note of this point. So now if I show you a cartoon of the detector, so you will see that I have a sample, which is a simple sample like a glass with some material on top. It could be semiconductor or anything else. What I do is I shine light, similar to what I did in the normal absorption case. But here I don't entire white light spectrum at once. I do it one wavelength at a time. Okay. So let's say I shine one wavelength and the sample absorbs some light, and whatever it didn't absorb would go through. Okay. So if you had a side, you would measure the transmission. That's how the other spectrometer works. In this case, what we do is this absorption would lead to that non-radiative decay in some way, and that will lead to some heating in the sample, right? So that heat is what I have to measure. Now, if I had a sensitive thermometer to measure that slight variation in heat compared to room temperature, I've used that. But I don't have such a sensitive thermometer because the heat I'm trying to measure is in nanokelvin to microkelvins range. It's very small. So you don't have such a sensitive. So what we do is we make use of mirage. So how we do that? We essentially have a sample that than the surrounding. So you have a delta T, which is a temperature difference, and that temperature difference induces that refractive index difference, which causes that mirage in the first place. So here we use that mirage and basically use a laser beam. This laser beam, nothing fancy. It passes on top of the sample where you have this heat. Okay. And if you have a heat difference, you have a refractive index difference, and the beam will deviate. Okay. If you don't have any absorption, it doesn't result in any heating. The delta T is zero, so the laser goes straight through. There's no deviation. So what we are essentially doing is for every wavelength light what we shine, we are measuring how much deviation do I observe in the laser beam. It is simple photodiode, so there is no fancy detector here. Now for whatever wave in here, there will be a specific absorption and there will be a proportional heat, and that will basically proportional deviation in the laser beam. And this now, if you sort of think of a typical absorption based spectrometer, you're limited by the detector that you use. So basically, your detector, if you use silicon, you can measure from like UV up till like or so, and beyond 1000 you cannot measure. And if you want to measure something beyond 1000 meters, you have to use either lead sulfide or in gas detector, which can do up to maybe 1600, 2000. Beyond that, again, you have to change the detector to maybe germanium or some antimony based detector. So here what happens is you need multiple detectors to measure the absorption in a traditional spectrometer. Here the detector is simply looking at deviation for the light that is incident on the sample. So you are detector limitation free in this measurement as compared to the traditional way of measuring absorption. So we can then measure a large range of absorption, the range which we can measure, 380 to 2000 nanometer. And this comes from the whole optical setup that we have for not a detector limitation, it's the excitation limitation. So all the lenses, fibers, light source, what we use results in this range. I could easily go to some other range as required if I can just change those optics. Detector will remain the same. Now the major advantage of this over the traditional technique is sort of shown here. So what you see is there, I have a film which is a perovskite film. If you don't know, just consider it as a film. And it has its own absorption spectra. So that's in the purple, which you measured using a traditional spectrometer. And what you see here is the data is plotted on a log scale, usually plotted on a linear scale because you don't have much sensitivity, so you only measure the linear. Now here I have plotted on a log scale to show what is the difference between the two. Here you see a small bump here, but it sort of plateaus out. But the PDS, what you see is you can go down almost like 6 of magnitude. And why this happens is because PDS exclusively looks at the heating, and heating only happens when you absorb. But if you consider optical absorption, as in the transmission based measurement, you can that light may never come through because it was not absorbed or absorbed, but it can get scattered away all around, it can reflect. So you have associated. It can be also wave guided, lot of things are there in the samples. So even if your sample is very scattery, the PDS can still look at it. Only measure absorption when you produce that heat, and that only happens not otherwise. So if you scatter light, reflect light, it doesn't result in any heat. Okay. So if your sample is 100% emissive, let us say, this technique is blind. And I'll come to this part in the last slide to show you how that is actually useful to study various phenomena. So, so for all those who are still confused, PDS is simple absorption measurement. It can do very sensitive absorption measurement, measure orders of magnitude. In fact, this level, what you see at the bottom, is almost parts per million level of absorption measurement. That's the sensitivity it can reach. So now there is theory associated from physics. I can give you the reference later if you want. You can read in detail. It's also the abstract file that I had submitted. So it's also there. You can read there. But the deflection, the angle of deflection is directly proportional to this term beta, the absorption. Okay. So there are a lot of other parameters. I'll not go in detail in that because the main case for me is to showcase the application, but focus on that part. So, so at IISc, we are basically building the second version of PDS, what I call it. This happens to be the only one in the world, not just in India. And it happens to be the only tool in India in some sense. So what we do is we start with materials, and most of you guys who are doing research or will be doing research go through this loop. So you have materials, you evaluate, you test, and you have some end goal in mind, and you make your and you spend some money and time on all this. So this is the ideal. But what happens in research is this: you don't not. You are basically stuck in a loop where you spend time and money from the point of view, time in your point of view, and PI point of view. So this is a loop where we are stuck. Now, how do you come out of this loop fast? That we are trying to do with PDS. Okay, we're trying to simplify the way out of this loop, and that is equally applicable to both as scientists as well as industry who are looking at new materials. If you were to plot cost and effort on y-axis, on x-axis, you'll see that material development, anyways, we guys do even in academia. But the time that you spend down the line is what you want to minimize. Okay. So what we do is we basically come in at a point when materials are made or process to basically develop alterations in the materials, and then what we do is the properties, and we basically help you determine which application can you go into, or even if you're going into certain application, what to expect out of it. Now, how is this all done is what the rest of the talk is focused on. So I'll just look at the time. Okay, so I see we are building the PDS 2.0, what we call. So usually the systems are used for conductors or thin films. We are going a bit beyond that. Look at so rapid screening. I just told you, we are trying to dependent studies. We're trying to look at temperature dependent studies. We're trying to look at magnetic field dependent studies while having the sensitivity that I just showed you. So we can look at various aspects, and I'll show you what are those aspects. Uh, okay, I'll skip that part. So films, well, there are a lot of highlights in this field. So you have solar cells, which are very efficient, closer to silicon. You have organic LEDs in the commercial applications in your phones, which have almost close to 30% efficiency, more than 30% efficient. And we are looking at optically pumped lasers, so you have in-house activity going on that front. And there's also field effect transistors, which we are trying to look at, which are the basic backbone of driving your and circuits that you have. Uh, in terms of issues, there are a lot of different aspects we focus in our research, and this is common theme across scientists in across the world. We look at earth abundant sustainable materials. That's a major theme nowadays. And what we would like to sort of do, because not just us, but the government is also wanting us to do, we want to have these scalable, translatable, where we can use these in industry. And for that, get scalability and reliability. So that is what the research focus across India as such nowadays. And there are also innovative device architecture one other aspect everyone is looking at. And in terms of cost is major thing. You want to sort of decentralize your manufacturing so that you can have this any manufacturing is possible, closer to the end use. And you're talking about having economy, which is more of not just making the material and using it, but also recovering it fully and again reusing it, kind of. So you have a loop there. Now I'll go into the results. We'll go to the application. So here what we're trying to look at is we're trying to look at a monolayer of a polymer, and what we're trying to do is measure whether I have a monolayer or not. Okay. To do that is you basically have a known thickness of a monolayer. So this is a say which says 20 nanometers is a known thickness, and this red supposed monolayer is a monolayer. Okay, and this is a spectrum that you get from a UVs, a traditional transmission spectrometer, and this is plotted on a log scale just for clarity. And you put the same sample in PDS. What you see is this is the red 20 layer showing the red absorption here, and the supposed monolayer is down. Okay, and absorption scales linearly with thickness. Okay, essentially know what is the thickness of your supposed sample that you're investigating. And so this sample actually goes into LEDs. So we want a very precise recombination layer. So we want it to be a precise monolayer where all the electrons and holes recombine to give you light. And we wanted to know whether it's a monolayer or not, because this is all solution processed, and it can result in several layers, or it can result in no layer at all because it's washed off from the layer. So before doing this, we monolayers in a synchrotron in something called as NEXAFS measurements. We could only do 20 samples a year because getting synchrotron access is very difficult. With these measurements and the sensitivity, we could actually do all these measurements in half an hour. So, and that's all in-house. So this was one of the first applications I ever explored, and probably one of the last things that I ever published. Not because I couldn't, but the author actually is no more with us, so we had to publish it in her absence as a dedication to her. Okay, so we did that in North Carolina, US, not in India. NextApps is not available in India. Probably do it in Diamond or in Germany, maybe, but it's mostly Australia as well. Okay, so this result uses the sensitivity part. Okay, so you have very weak absorption, you can still see it. That's what I'm trying to say. But if you look at UV-Vis, it sort of flattens out. You cannot see the features below the band. So essentially for all people here, we are looking at weak absorptions, not the strong absorptions. So you're focused more below band gap features or weak absorptions in general. Okay. So folks who are focusing on metal oxides are crazy systems. They just change by you, if you change the parameters or if you shine UV, you just change the atmosphere, you make it or you process it, things change drastically. So here is one example of a metal oxide, indium gallium zinc oxide, and what you're trying to do is you're trying to look at the states below the band gap and see how many defects you can see within the gap. Okay. So the red curve is for a sample which has been processed in air has oxygen. So you can see the red curve after the band gap, the absorption drops with some sort of slope here. The black curve is when we process additionally in a vacuum condition, so where there is deficiency of oxygen. So that can induce deficiency of oxygen in your sample as well. So what happens here is you can see there are new states come up in the absorption. Now, if you were to measure the same sample transmission spectrometer, you would have only seen up to 10 raised to minus 2 in this value. All this that I am showing you here. So what happens here is these states, and they're created, let's say the band gap is 3.2 electron volt. This these states exist all the way down to like 1 electron volts. So that is far, and these states essentially are detrimental to any electronic device. And when we ended up making FETs using this, the device is made out of this black sample here is all dead. There's Now you can do further measurements after PDS, where if you are interested to see the origin of these defects, you will need assistance. So PDS is the first step, and then it directs you to other sort of measurements. So we UPS measurements, which are basically measurements which tell you what is the valence band, and you can actually see this density of state is existing here matching with the valence band. So we know that these defects. So that is one thing. And then you can do other chemical measurements, NMR and so on, and then figure out what is the chemical origin of these states. Okay. So you can go in depth. But this is the precursor, at simplest precursor, because if you see these states, you cannot make a FET. That is clear. But if you see these states, for folks, I don't think any chemistry person is here, but if you see these states, chemists will be excited because for them they need defects. This works in both ways. So you want defects in some cases, you don't want defects in some cases. You can see them here pretty much. So then there is organic photosynthesis, which essentially works on combining two materials. So there is a donor, so-called donor and an acceptor. And when you mix these two, they basically give a layer that works as a solar cell layer. Okay, it's called a bulk heterogeneity. And if you look at the design, it looks like this, where the donor has the energy levels like this, and acceptor has energy levels like this, and this is a type 2 heterojunction, where you have a valence band of one semiconductor that is higher than the other, and conduction band of sort of semiconductor is higher than the next semiconductor. The difference is, if you absorb light in the donor, your electron can naturally go to the acceptor because of the energetic drive here, so it can go downhill. Hole remains here because holes cannot go downhill, they prefer to go uphill. So you basically have hole going back in the donor and electron going to the acceptor. Now if you can get these right, you will have your solar cell giving you current and you're happy. But in organic semiconductors, there's a problem, like the exciton binding really high. And what that does is essentially you cannot screen these charges even when they are in different materials. So remember that donor and acceptor are two different materials. You're just mixing them together. Okay. So even then, so when the electron enters the acceptor, it can be bound to this hole, and that is called a charge transfer state. And it only exists when you have a donor and acceptor mixed together. Okay. It doesn't exist. You don't have the donor and acceptor like system. If you only measure acceptor, you don't have a charge transfer state. Okay. This is an intramolecular state. Okay. So this only exists when you mix, and the existence can be confirmed in the absorption. So when you see, if you were to simply talk about absorption, these two things, you will say that okay, the resulting absorption may be just summation of the two absorptions. But in this case, that's not the thing, because you also have this new state across two materials, an intramolecular state, which shows up in the lower energy. And that state is extremely important because that is what determines the voltage that you get in your cell. So if you were to make materials, and if you're interested to make efficient solar cells, like I am interested, most of the folks who work on solar cells are interested, you need to know what are your limits. Okay. Let us say if you were to blindly just make devices and you hope that you can improve by doing some processing changes, that may not be working always. Because if you are already at the limit, and the limit is defined by this, which is an intrinsic property of this material combination, that is what you should know beforehand. So we can tell precisely what's the energy of this state, and hence what's the maximum voltage you can derive from such a material system before you make a device out of it. Okay. So this is how the PDS helps. Uh, and then if you have semiconductors, well, you can sort of dope your semiconductor for various applications. And for semiconductor application, you need fast transport, fast switching. If you're talking about displays, you talk about resolution displays, 4K displays, where you need fast switching LEDs. And the driver to that is a fast switching transistor. And that needs materials, you need very fine doping, very controlled amount of doping. So what you can do is, instead of making a device and understanding what's the level of doping that has actually resulted after you have done the process, you can essentially measure absorption and look at the doping peak. And this is a polymeric sample, a p-type polymer which has been doped, and we can precisely see the absorption from the doped state. If you know the absorption cross section, you can measure the quantity of doping in your material. Okay, so this is one of the use cases that you can do. It just helps how much doping is there. You can of course reconfirm the same using a device result. That's also possible. But this is the most easiest thing because you're just making a film after all, not making a device. So, so one other thing I would like to showcase here is to some more fundamentals. Yeah, I'm on time. So this is the absorption spectra of photosystem 2, which is essentially a part of your chlorophyll. Okay. So these are also natural systems, these are excitonic systems. So these relate to the organic semiconductors which we make or use. And what you see here is this is the absorption peak that comes in. So this is your excitonic peak. You also have some other excitonic peaks here. But what I want to show you is this excitonic peak is pretty clear. It's like a sharp peak. You can see it very easily. And this is visible when I mentioned earlier that I am only looking at non-radiative relaxation. Okay. So imagine that most of the physicists here, if you see an exciton, you will relate it to radiative emission, right? Natural systems don't do that. If a plant were to absorb sunlight and emit light, it would have been fine, right? We would have not been existing here. So they don't do that. In fact, most of the light absorption goes into non-radiative pathways, and that's where they make the food. All the reactions happen there. So here, because of that sort of thing, you can see the excitonic peak even if it is non-radiative, okay, and not so much radiative there. So now if I go to other systems, perovskites, now here these systems also show a huge excitonic absorption, okay. But there is one peculiar thing, and this is something we are looking at right now in our group. So if you see this purple sample here, you will see this is an absorption curve in a normal absorption spectrometer. So you can see very huge absorption curve here, and this is related to an excitonic absorption. Okay, that happens because the binding energies are very high. Happens to be a 2D perovskite, very high binding energies. Now, if you compare the corresponding PDS spectra at the bottom, what you notice is very unusual thing. Do you see a peak here, the purple sample? You don't see a peak. Why? Now, you would argue that if absorption is showing you a peak there as an excitonic, very strong peak, and we are looking at only weak signals, so such a strong signal easily show up in PDS. But that doesn't happen because in perovskites, class of perovskites, it's very peculiar that these states, excitonic states, are extremely emissive in nature. So what happens is the absorption that happens in these states, the excitonic states, emit lot of light. So they don't result in non-radiative relaxation. So hence what you see in PDS is a continuum of states. You don't see the excitonic states at all. So we are basically trying to develop a model using this particular phenomena because we are exclusively looking at non-relaxation here. So let's see where that leads. So this is one classic case of use of this system. Okay, so one last aspect before I switch to the other basic. So this system actually measures heat, right? I told you it measures non-radiative relaxation. And heat basically diffuses out of a material at a constant. No matter what light you shine, you produce some heat, and that heat diffuses out in a specific pace, and that parameter is called thermal diffusion coefficient. And in every material, that's a constant. It doesn't change. It's not very permanent. Absorption is, heat is not. So what you can do here is if you have heat diffusing, if you have, let's say, absorption happening on the top of your sample, this is the top of a sample where the laser is passing in front of it. The heat diffusion from the top to the surrounding is extremely quick because it's happening right at the top. But what if it inside the sample? So if it happens, let's say in the back side of the sample, it will take the most time to diffuse from the front. And if it happens all the way in the bulk, it has a certain time constant associated. Okay. So now what we can do is we can basically use this particular factor and assign the absorption to a certain depth in the sample. Okay. So let us say if your sample is 100 nanometers thick and you can, so in the measurement we actually can measure the phase angle with respect to what we excite the sample with. So essentially it gives us information about what depth the absorption is coming from. Okay. So based on that, we can actually tell whether qualitatively we can tell whether the absorption is happening on the top of the lattice or the back side of the sample or in the bulk. This differentiation can be easily given for all measurements. But if you can precisely place the absorbing layer in different depths and you can do a systematic study, you can actually do a depth profile using PDS in a systematic way. And such a depth profile is not possible with any standard technique. So this is one major advantage that you can get, and a classic example of this is, so we take two polymers over here. So it's a busy slide, so I'll explain. So these blue curves are absorption, these red curves are the phase associated with the signal I'm measuring. Okay. So usually when the absorption is coming from only the bulk, the phase remains constant because the heat diffusion is same for reactions that happen, because it diffuses all the way from the bulk, it has the same sort of phase constant. So the depth profile basically depends on the sample being optically transparent. So the condition we place while doing is the alpha absorption coefficient multiplied by the thickness should be less than 1. Uh, that depends on the calibration. So if we properly do that, we can go to that depth for sure. But we have not done it yet. So here what you see is these two samples have this absorption edge, the absorption drops, and there is remnant absorption here. This is an unwanted absorption. So these are, I can attribute this as defects. But when you look at the phase angle for this particular sample is this. There's a small rise here, not much in terms of angle, but the other sample, the phase rise is huge. Okay. So what this corresponds is, this corresponds to the absorption from the top of my sample. So if you have, let's say, inorganic semiconductor, it's known that the top of your sample is not saturated. So if you make gas, if you are terminated with gallium, you have to passivate it with certain agents. If you are arsenic terminated, you passivate it with certain other agents. So you know the surface is where the cut is. So this measurement can precisely tell you that part. And then you go ahead and do passivation strategies as such. Okay, so some theory. I have 10 minutes, I guess. Fine. Okay. There is a parameter called Urbach energy, which is associated with the absorption equation. Okay. So if you look at the absorption equation, it basically exponentially dependent, and in the numerator here is the EU, the Urbach energy. So if you pull that out, it's nothing but the slope of this absorption curve that you're seeing here. Okay. So if you curve on a log linear plot and you take an inverse of it, that's what gives you the Urbach energy. So the way to see this for those who are confused is, because if you have an ideal semiconductor, what you're looking for is an that ends at a point which you call the band gap, and then there are no states below that. So you want a step function like absorption, but we don't have that, and that's why scientists sit here and work on materials, thankfully. Otherwise, we wouldn't have jobs. So because our materials don't have this idealism, so we have different states below the band gap, and we would like to quantify like to minimize these states. That's what we do in our research in semiconductors. But for people working on catalysis and other aspects, they want to maximize those states. So there's a there. So this parameter here essentially tells you what's the steep and how it converts into a value. So you can, instead of qualitatively slope is very steep, I have less defects, you can assign a number to it. Okay, so you can quantify. So for amorphous silicon, you can quantify it as, sorry, you're asking something? Okay, no. So for amorphous silicon, you can quantify that as 50. So this is the graph for amorphous silicon. So you're essentially looking at these states and you're assigning a number to it. So for easy sort of reference, if you have higher Urbach energy, you have more defects, disorder. If you have lower Urbach energy, you have less disorder. Okay, so you want to minimize this at a semiconductor. The contrary for the other folks who works on catalysts, who are different. So if I show you a comparison here, so here I have three classes of semiconductors. So PTB7 is an organic semiconductor. Perovskite is a hybrid of organic inorganic. Gallium arsenide is a well-known inorganic semiconductor. So if you measure the absorption for these three, these are the three parts. So you can easily say that gallium arsenide has the sharpest drop in absorption, so it is less defective. Of course, we know that. And if you look at organic semiconductor, the tail drops in a shallow manner, and these are more defects. And perovskite is somewhere in between. So that there. So if you plot the Urbach energy on y-axis, you can see organics has more disorder. Perovskite has somewhat less than that. Gallium arsenide is the lowest among the pack. And before I make solar cells, I correlate the voltage that I get in my solar cells. So you can see, so the real voltage that you get in a solar cell ideally should be equal to your band gap, but there's always a loss associated with that. If you correlate the Urbach energy with respect to the voltage loss that you have with respect to the band gap for any semiconductor, you see that lower the Urbach energy, lower this loss. So that is a very easy correlation to establish, right? And if you FETs, you basically do a lot of painful work to measure the subband gap density of states. This was one of my first papers, actually, ever. What we did here is we basically measured FETs using all these organic semiconductors, and measuring FETs at various temperatures takes months, not days. And we did on the same films, just optical measurements in few hours. And what we find is there is this T naught, which we measure for most of the FETs, where we try to estimate the subband gap density of states, which basically determines the mobility of your carriers inside semiconductor. So you want to minimize this. So hence we want to sort of measure a mobility and then measure sub-gap density of states and say that, okay, how can we improve on this, right? And this work of time. Now what we found surprisingly is this parameter is exactly equal to Urbach energy error range, okay, which is not unusual because in Urbach energy you are essentially looking at the density of states below the band gap and you're trying to quantify the width associated with. So this relates directly. So this helps because before even making FET, you can take your material and what Urbach energy it can demonstrate and what potential application it can have in FETs, how much kind of qualitatively. Now coming to some other classes of polymer. So this is a class of polymer which we sort of looked at in around 2013, 2014. And this had a peculiar feature. This had a backbone that was very rigid. So it's like your motor, you can drive fast. And it, in terms of classic semiconductors, which were old, there you used to have roads like city roads where you have sharp turns, you have to slow down before you turn, less. But in these polymers, what we found in terms of modeling is they basically have a rigid, so the bending radius is quite large, and hence you don't experience that slowdown in the mobility. Okay. But this was done post measuring PDS. So what happened was we started with PDS usual as a diagnostic technology, and we found that this particular semiconductor ideally has a steepest slope. And this was the first time we saw such small disorder or urban see that the Urbach energy is close to 20, 22 milli electron volts. And you have the thermal energy of 25 milli electron volts at temperature. So you can imagine you have certain amount of energy at room temperature and order here is less than that. So that enables kind of like transport. And that sort of then got, so we went material studies where we found that it comes because of the rigid backbone facilitating the transport. And so this can sort of correlate to kind of small potholes and you being on high speed on a highway. You never experience the, okay. So this was the first material which demonstrated a mobility of, and that being an amorphous semiconductor. Okay, this was not based on crystalline because the side chains here have 16 carbon atoms on both sides. So it could never crystalline. So then this material class now rules organic solar cells field because this class has been translated to N-type semiconductors, which have replaced the traditional fullerenes, the buckles that you had. And hence you have the rise in the photovoltaic efficiency going beyond 20. They were stuck below 15, now they go beyond 20, just because of this particular innovation. And this all started with PDS. So I'm sorry about that. Now, for people who make nanocrystals, you can essentially see the passivation effects and look at the Urbach energy. So I'll with this data. Uh, Let me see what other applications I can show you. Wrap up in 5 minutes. So some of want to measure polarization. They want to make their samples oriented. What you can do here is so this kind of a substrate where you can essentially have model the fluid dynamics, and if you take a solution process semiconductor, you can squeeze them between these vertical bars and they try to sort of crystallize in some direction. Even otherwise, if you make nanowires, they're crystallized in one direction. So you can assume that as. So now if you take that as a sample, along the growth direction, you will have better crystallinity. So you expect better transport. Perpendicular to the growth direction, you don't expect better transport. So that is precisely what here. So if you basically polarize the light perpendicular to the sample and disorder, the disorder comes higher than the polarization along the growth direction. And here obviously the disorder is low. This shows that you have a material which is not isotropic in nature. You do have a disorder that is sort of anisotropic in a way. Okay. And if you make devices out of it, you will see the sort of performance difference in that aspect. So that is that. I'll not bore you here with this. But yeah, this is one other important aspect you should know. So measuring sensitive absorption, I have told you PDS can do that, but you can do the same using many other techniques. They do exist. The most standard technique is current measurement, and it's done in the Fourier domain. So it's called Fourier transform spectroscopy. Okay. So simple photocurrent measurement won't work there in the Fourier domain to gain the sensitivity. So let us say semiconductor, I showed you a simple picture where a semiconductor didn't have any doping to start with. Okay. If you had doping, you would have a free carrier. Maybe let's say it's in the conduction band, and you have an associated ion sitting in the valence band, which is a fixed ion. It cannot move. It is fixed in the structure. Now, if you bring light, so let's say if you have a photon energy that can, the free carrier will also absorb light. What happens when a free carrier, it will go higher up in the manifold of the conduction band, and then if nothing is there, it will relax down non-radiatively, and that's all happens. But if you have a system where you want to measure photocurrent, when does photocurrent happen? When do you measure photocurrent in the external circuit? When you have both a free electron and a free hole coming out of the material or your device. Okay. So if you have doping, you have a fixed ion and you have a carrier, and this free carrier absorbed that photon. It just went in energy and then relaxed. So there is no extra that was generated. So you cannot measure photocurrent. Doping, you cannot measure photocurrent. So your photocurrent method is blind. Okay. So this is one classic example. So if you take perovskites, the non don't have any remnant doping to begin with. So if you measure PDS, you measure the photocurrent based technique, which I call EQE here, see the same absorption, the same results, Urbach energy is same, not different. Okay. But if you go to samples where you have doping, what you will see is the photocurrent based method doesn't see. So you end up measuring a different absorption curve here or a different profile, and the PDS measures something different, which is on a of absorption. So this shaded region is the absorption coming from the doped species absorbing light. Okay. So then you consider the Urbach energy. How many of you test your knowledge? So how many of you think the Urbach energy should include this doped states? How many of you think not? So if you can raise hand, how many of you think they should not include dope? So how many of you think it should include doping? Arre, I am sort of boring you guys, it seems. You're sleeping. I know it's a late evening, but I'm giving you simple examples here. So anyways, so point is doping, and for people who work on semiconductors, this doping acts as. So if you talk about transport, that is not a desired feature. So if you want to talk about disorder or Urbach energy, it should include that because that actually is a factor that reflects disorder. Many papers don't include this, and I have pointed out to others who are placed at very well, they have acknowledged that. Because when you measure the disorder using photocurrent, you should explicitly mention that we have done this using photocurrent, which doesn't measure the contribution of doping. That is okay. Material is excellent because the disorder is low, but the device, and why is that the case? They don't explain. Okay, case here. So I'll probably stop at that point. I have some perovskite results where I see dynamic absorption shifts, where basically shine light. So this is a halide segregation effect that you have. And coming to some recent thing, recent interest of mine, where what you saw now as a PDS is a transverse PDS. So my light was coming in this direction, my probe is going this direction. So it's called a transverse. So there's a 90-degree angle associated. But in this scenario, I cannot measure liquid samples. I can only measure solid samples. So if I want to measure liquid samples, and why do I want to do this? Because if you do sensing, classic case, COVID, what did you used to do? You gave your sample, PCR hota hai, you get a result, and in there was a value, CT value. If you ever noticed that, that CT value essentially is associated with a process behind. So what used to happen was you have some molecules which you put into your biological sample, they go and attach to the protein. And when you have a COVID and that protein is there, this molecule will go and start glowing. It will start emitting radiation. Now for emitting radiation, you need a laser to excite it in the first, photodetector in the other place, then you measure. So if the count of virus is less, you amplify that. So that's the CT value, how many times you amplified. And there was a limit associated set by the government that, okay, if above 50 times amplification, your patient is not very serious. वो चलता है, COVID भी है, चलेगा. Yes. So this biosensing actually happens through radiation measurements, and most of the biosensing happens that way. Because what is needed for biosensing is sensitivity and selectivity. Because first you want to detect traces of presence of any biological element. It could be COVID, it could be whatever. Okay. And you want to sort of have selectivity of measuring, because you don't want to say that when you don't have cancer. So you need selectivity. So now the why is absorption not used for that? So the prime reason is absorption doesn't present sensitivity. It may have a selectivity because they are spectrum associated with some absorptive features, but it doesn't have sensitivity. So my interest is to develop this technique to use the sensitivity I have, whatever spectral selectivity I can achieve. Let's say if the COVID protein may have a separate absorption feature, measure that, then I can do the measurement label free. I don't need any extra molecules. I can just measure things at the source where I collect the samples. One of the things which I'm interested to do using the technique. But for that, this measurement doesn't work, the transverse measurement, because here what happens is the sample, the laser is going on top of my sample, and my sample, if it is liquid, it has to be enclosed in some, and my laser cannot go in at the edge of the container. It has to be closed. So now what I do is I flip the system and I go in mode of PDS. Now what happens here is the excite and the probe laser both are in the same direction. Overlap inside your sample. So now the interaction of these two lasers is happening inside your sample. And again the same principles apply, and you can measure liquid samples. Okay, so we are basically modifying a tool to do this and then evaluate certain things. Yeah. It is inside the sample, but chosen to not being absorbed in the sample. So the probe is current within the sample. The only absorption will happen because of the excitation laser. So let us say if you know what wavelength to excite for the spike protein, you excite it with that, and then you choose a laser wavelength which is independent of that and is transparent for the measurement purpose. Deflection as such. So this is the collinear mode. So we can do is one example of that where you can see liquid samples sort of being measured at different temperatures. So I'll basically stop at that because there's a lot of other things also you can do. I'll stop here and I'll summarize what I just spoke. So in a nutshell, what I tried to present to you is a technique called PDS, and it essentially is an absorption measurement technique. Very, you can measure several orders of magnitude of information, and essentially be used to do a lot of different measurements related to semiconductors or in general. And those measurements can act as the first step before take the next steps. So this is an additional step for people who do research. Try and minimize your wastage of time, if I were to say it that way. Maybe PIs say that's how the researcher matures, but it's everyone's take. So yeah, so we can do that. We can measure different phenomena, and we can also venture into biosensing. So that's all. So this is our group. So thank you. If you have any questions beyond this talk, basically contact me on my email. Okay. So thank you.
Thanks, Aditya, for interesting talk. So now the session is open for the question and so someone could you please help me to transfer the mic? Have any questions?
Maybe I was very clear, or
Yeah,
it's the
it
wrong
was
time
clear.
to be
It
here.
was clear. First of all, nostalgia in the sense, where is this building located at ISC? From the IPC department,
Okay,
the
based
old
on
one?
the bigger map of.
Yes.
This is basically near the D gate.
Near the D gate, I
Yeah.
see. Okay.
This is the World Trade Center beyond Columbia.
Okay. Recently, I've been familiarized with the chemical science department, which is new. That's
So we are just adjusted to
to that.
across the road.
Okay, cool. Great work, great spectroscopic technique. The way I see this, you're well suited for thin films as well as you're working on.
Sure.
These thin films have to be really very correct.
Not necessarily,
We
because
can make rough films and you should be able to tell us.
should be fine. Roughness
you will
should be within hundreds of microns, which
Hundreds
is
of microns.
usually the case. I mean, if you give me stones which are
No,
millimeter
absolutely
height,
not. Huh.
that won't work.
The
So there's nothing like that, because see,
Yeah.
what we do as such is, so if you usually this technique is used to compare between different processing or different set of samples. And what we try to do is we try to maintain the probe beam several tens of micrometers away from the sample. So even if your sample has
I
tens of
see.
micrometers,
It's not really grazing the
no,
surface.
not really grazing. We
I
can
see.
be away. The only thing is heat signature falls exponentially as you go away, but you can maintain that separation
I
precisely.
see. So that's good.
Then how much the delta theta deviation of the laser?
So the deviation will sort of, it's the distance. So we try to
because of
set
the
a
delta
distance.
T. Yeah, that is.
So that will also be in the range of nanoradians and so on. So
Okay,
it's
yeah, it
not
will be
very much
very
sensitive detector. So
Yeah,
the electronics
that
is where the whole fun is.
so very tricky.
You can
Yes.
do it, pick up the larger lateral
Larger.
deviation.
Great. I come from a little bit of perovskite background, although what you have shown us is mostly the 3D and the 2D systems. Relatively easier to make thin films, where I do is 0D systems.
Okay.
Not so easy to make thin films, but we'll talk more.
Yeah.
Very nicely pointed out how you can look at the doped system. With this every day, my students always curse me because I'm telling them really. The issue is sometimes in this doped system, and anybody can come anytime when you guys are bored and when you have any more questions. Yeah, because I'm taking the liberty. Yeah. So when we look into these zero, go in extensively into doping, and we can start hosts which are not that emissive, and then bring in highly emissive dopant systems.
Sure.
Sometimes, if it's not that clear, we sometimes end up having emission and we cannot assign it to one species.
Yeah.
You've shown nicely how you eliminate which absorption or which emission is not causing the emission.
Yeah.
That's one way. Use PDS in together with, say, a simple absorption measurements.
Sure.
Which is probably aided by the photoluminescence excitation that we do.
Yes.
Can actually help us a lot in assigning what is my emissive species. So I will send samples to you.
Precisely that exciton that I was talking about is actually in that.
It is meant for that. I see that as a great avenue because we are struggling with that in terms of some samples. So that's actually very good, and we will talk more.
Sure, definitely. And also, just to extend that discussion, so this also applies to organic semiconductors,
Yes.
where you have triplets, which are usually dark.
That was my third question. How do you get to dark states?
We have darkness is basically just related to a lower absorption coefficient.
Coefficient, yes.
It's just that. So we did managed to measure the triplet state direct absorption in a pentacene system, but then we had to do a lot of different jugglery in the sample that we made. But it is all published. So we actually had measured the absorption in pentacene. Now, what is of interest to me, when I said I'm doing PDS 2.0 and magnetic field being one of my handle, it's actually pointed towards that, to see whether that has an influence for me to see the triplets directly.
Right.
As such.
So, a lot of opportunities, and hopefully we can talk more.
All these. So
Yeah.
let's see.
By the way, that's it.
I'll go step by step.
How much did you guys spend in developing this setup, the PDS-1, roughly?
That's a secret question. So.
It's not an RTI, I know. It's not secret.
So, fine. I mean, so at ISC, we have been given startup grant. So what we did was we tried to build the PDS, and we have also subsystems around it, which can help in the in situ measurement. So a typical PDS system, if you were to ask frankly, you can get 3 to 4 orders of magnitude, and that can be built within 50 lakhs easily.
Okay.
In fact, if you are frugal in using which monochromators you use and all, that's the major cost. Monochromator and lock-in, nothing else is costly.
I see.
In fact, xenon lamps and all you can phase out, you can switch to LED. It is very much possible.
Cool. Great. Thank you. Loved it.
Yeah. Hello, sir. Nice talk. I have one technical question. The surface stability, how stable it is? Like there, if you are saying it is in nano Kelvin, in one sense, the position wise, stabilities and temperature wise, because in which condition, background temperature, and in that case, I'm asking.
Sure. So the surface stability, if you're asking me from the sample point of view, that is not an issue because we have all dampers fit inside the system. So the noise will be extremely low. Okay, so the vibration is extremely low. Now, if you talk about and also one more thing, these are done at very low frequencies. So it's almost quasi steady state. So all the fast vibrations don't affect this whole measurement. Now, if you talk about the stability of the measurement, which stems from the laser, then the laser itself is designed to have ultra high stability. So these lasers which have very high pointing stability. I mean, the parameter off my head, I don't know the unit, but it's extreme lowest you can actually have for a laser. Only thing is these are CW lasers, so these are not pulsed lasers. There's the pointing stability. The cavity is very stable in terms of the emission. So the other question was about
Temperature.
Temperature, yeah. In terms of so your question was about the temperature range, or
so I'm
the
talking about
external
the
temperature
fluctuation,
stability.
fluctuation of in
Okay.
the system.
So see, the external temperature fluctuations don't affect so much because they don't happen in, let's say, a few hundred milliseconds. So usually there is a inertia associated with the temperature change, and that is this room. This room temperature won't change suddenly. There's always a steady rise. So we basically enclose our system within a temperature insulated sort of enclosure. So this is essentially those tools that you use for acoustics. If you go to a studio, you'll see that the acoustic setup is such that you don't hear your voice resonating. That is because you have the acoustic foam associated there. And that same thing works for even the temperature. So we use those to basically minimize any fluctuations in temperature.
So it is like
so even if the temperature changes, what happens is your zero position of the laser on the detector is what changes. So that automatically gets zeroed on every measurement cycle. So every laser fluctuation that you see is essentially zeroing the zero position. So that happens at every 100 milliseconds times.
So every time you are checking the background and then you are.
Yeah.
Thank you, sir.
Yeah.
Primarily a steady state measurements. If you really wanted to invoke time resolution into it, what would you comment?
We call it time resolved PDS.
I'm interested in the time resolution that you have.
So precisely this measures thermal diffusion directly. So this is probably the easiest way to measure thermal diffusion coefficient. Beyond that, so if you stay on one length and you change the frequency, you're changing the time associated with the carrier and excitation at the same time. So in the initial time scale, your process is more thermal diffusion dominated. And in the later time scale, at a faster time scale, your process is more recombination, carrier transport dominated, diffusion dominated. So that is where these two into picture. So this is heat diffusion dominated, electronic contribution. So if you were to measure this, associated, and you can measure parameters like minority carrier diffusion, thermal diffusivity, and these are all like measured for silicon, and they are pretty much in sync with what are the measured values. This is what you can do. Yeah. So it's a versatile technique in a way.
Hello, sir. So I have a naive question. That is, you have the sample. Okay. So now, if the sample is made of two junctions, means two different kind of bodies. One has more doping, and one has less. So how does it affect the mirage angle, and how you detect that which part is causing how much defect? Or so you
in
do it
terms-
separately. Then you
No. So basically, if you have these two present in the same sample, you cannot spectrally distinguish. It all depends on absorption. So basically the summation, unless there is a spectral separation in those two absorptions, then you can do that. So the result I showed you where I said I measure monolayer, that actually was made on an organic semiconductor. So the way we did it is we had a base semiconductor, we put a thick layer, a spin washing, which we should basically remove everything, but because of the pi stacking interaction, there remains a monolayer back. That was our hypothesis. That was true. So we can measure that because the first base semiconductor is UV. That doesn't affect our measurement. The other one has a spectrally see that.
Okay. Thanks.
Thanks.
Okay. Any other question? Okay, if there is no other question, so once again we will thank our speaker. Okay.
Thank you guys for staying on evening.
Yeah, today it's a little bit different experience. That's why if theory means many students will be here, the experimental, that's why maybe the less student are bored with the yesterday's talk. So that's why maybe less.
I mean, I can tell you that the forcing theorists also go into experiments.
Yeah, we
That
should.
ratio will change. What?
Okay. Yeah.
Okay.
So just a note of thanks.
Yeah. Thank you. Thanks. Thanks a lot. Thank you, guys.